Hello everyone, my name is Cyra Natanya Evangelista Oroh, and in this opportunity I will give an explanation about saturated vapor pressure. The origin of saturated vapor pressure, and for the first one we're gonna start with the evaporation of a liquid. The average energy of the particles in a liquid is governed by the temperature. The higher the temperature, the higher the average energy. But within that average, some particles have energies higher than the average, and others have energies lower than the average. Some of the more energetic particles on the surface of the liquid can be moving fast enough to escape from the attractive forces holding the liquid together. They evaporate. The diagram shows a small region of a liquid near its surface. Notice that evaporation only takes place on the surface of the liquid. That's quite different from boiling, which happens when there is enough energy to disrupt the attractive forces throughout the liquid. That's why, if you look at boiling water, you see bubbles of gas being formed all the way through the liquid. If you look at water, which is just evaporating in the sun, you don't see any bubbles. Water molecules are simply breaking away from the surface layer. Eventually, the water will all evaporate in this way. The energy which is lost as the particles evaporate is replaced from the surroundings. As the molecules in the water jostle with each other, new molecules will gain enough energy to escape from the surface. Next is the evaporation of a liquid in a closed container. Now imagine what happens if the liquid is in a closed container. Common sense tells you that water in a sealed bottle doesn't seem to evaporate, or at least it doesn't disappear over time. But there is constant evaporation from the surface. Particles continue to break away from the surface of the liquid, but this time they are trapped in a space above the liquid. As the gaseous particles bounce around, some of them will hit the surface of the liquid again and be trapped there. There will rapidly be an equilibrium set up in which the number of particles leaving the surface is exactly balanced by the number rejoining it. In this equilibrium, there will be a fixed number of the gaseous particles in the space above the liquid. When these particles hit the walls of the container, they exert a pressure. This pressure is called the saturated vapor pressure, or also known as saturation vapor pressure of the liquid. Next, we continue to the variation of saturated vapor pressure with temperature, and it's about the effect of temperature on the equilibrium between liquid and vapor. You can look at this in two ways. There is a common sense way. If you increase the temperature, you are increasing the average energy of the particles present. That means that more of them are likely to have enough energy to escape from the surface of the liquid. That will then increase the saturated vapor pressure. Or you can look at it in terms of the Chateliers Principle, which works just as well in this kind of physical situation as it does in the more familiar chemical examples. When the space above the liquid is saturated with vapor particles, you have this equilibrium occurring on the surface of the liquid. The forward change, or liquid to vapor, is endothermic. It needs heat to convert the liquid into the vapor. According to Le Chatelier, increasing the temperature of a system in the dynamic equilibrium favors the endothermic change. That means that increasing the temperature increases the amount of vapor present, and so increases the saturated vapor pressure. And for the last topic, it's about the effect of temperature on the saturated vapor pressure of water. As you can see the graph here, this graph shows how the saturated vapor pressure of water varies from 0 degrees Celsius to 100 degrees Celsius. The pressure scale, or the vertical one, is measured in kilopascals, or kPa, and 1 atmosphere pressure is 101.325 kPa. I think that's all the explanation about saturated vapor pressure. Hopefully you guys can be understood about the material that has been explained. So thank you and see you.